Hello and welcome, ladies and gentlemen, to this edition of our global webinar series. Today's topic is safety capacitors, battling EMI and preventing harm. My name is David Adib, a senior technical marketing engineer here with KEMET in Florida, and I will moderate the webinar today. We're very pleased that you find time to join our webinar. Our presenter today is Sam Accardo. He is KEMET's field application engineer. With this information, I hand it over to Sam. Hi, Sam. Thank you for your time today. Please tell us a little bit about yourself, introduce yourself to the audience, and then begin your presentation. Thank you.
Thank you, David. Hi, everyone. As David mentioned, today we're going to be talking about safety capacitors, in particular, battling EMI and preventing harm. So a little bit about myself. My name is Sam Accardo. I've been with KEMET for a little over 3 years now. I'm a field application engineer that covers the Northeastern Territory, which is the Northeastern United States and Eastern Canada. And I guess a little bit of background about myself. I'm a graduate of Louisiana State University with a Bachelor of Science in Electrical Engineering and a Bachelor of Arts in Mass Communication. And I know it's not something that we typically do, but from right off the back, we're going to go ahead and start off with a poll question. And I'll let David go ahead and read that aloud.
Okay, so the first opening question for today is, before we begin this presentation, what is your level of understanding of safety capacitors? Please note that this is a multiple choice question. Please read the different options and submit your answer accordingly.
Thank you. So I guess a little bit of background for everyone. I just kind of want to know who I'm talking to today and make sure that we're answering the types of questions that you want. And then it's also good for us to know who's attending these types of webinars so that we could plan accordingly for the future.
Okay, so I see that about 10% of our audience today have selected option A. Safety capacitors are a new subject for me, while almost 90% of today's audience selected option B. I have a basic level of understanding of safety capacitors, with just a few selecting option C. I know more than the presenter.
Awesome. Well, thank you, David. There's no right or wrong answer for this. I just want to get an idea of who I'm talking to. So it sounds like a majority of you, have a little bit of an understanding. So I guess let's go ahead and jump right into it. Why is this not clicking? There we go. So for today's outline, we're going to basically be talking to you about safety capacitors and AC line filters and, the things that you should really know about. And so we're going to talk about the electromagnetic compliance, also how lightning strikes can harm the equipment you have in your house. We'll go into detail on what safety capacitors are, how to remove EMI on an AC line. We'll talk about the subclassifications and substitutions for the safety capacitors. And because automotive is a very big environment for KEMET, we're going to talk about some automotive environment as well. And then we're going to talk about the safety capacitor types. Typically, they're film or ceramic. And then finally, we'll talk about a few of KEMET's product offerings and some of the highlights. So starting off with electromagnetic compliance, I first think it's very important to tell you what mains or main voltages are. That's basically the electricity or power that's coming to your house from the power lines outside. And basically, that power runs all the way through your house. So it's going to go to every single appliance, every single thing that you plug into the wall. So think your washing machines, your stoves, your microwaves, but also your laptop, which is probably plugged into the wall right now, your cell phone, all of these things plug into a wall, even your lights plug into a wall, and the electricity that's flowing through your house is flowing to each and every single one of those devices inside of your house. So essentially, it's a huge power network, and essentially everything that happens on that network can affect other devices. So you have to design an AC line filter in order to, one, keep out the bad stuff from disturbing your device, so causing interference with the devices that you're using, but also the AC line filter has to be designed to keep other devices from being affected by your devices or by one device from another. So it's very important to isolate the devices as well. And then one other thing I kind of want to point out here is that when you're designing, I guess, a AC line filter, it's also very important to know where you're designing it for. So typically in the US, we design 120 for 60 hertz, 120 volts AC, that is, for 60 hertz. But in other countries, such as, well, for example, Europe in general, Europe does 220 for 50 hertz or 60 hertz. So it's also very important to know where you're designing for these types of devices. So that's a little bit about electromagnetic compliance. The types of devices that you're designing for have to be able to, again, isolate the device where it's not going to harm other things on that same network. And you also have to keep it from being harmed from all of the bad stuff that's coming in. And it also has to do one other thing. So typically, there's going to be some type of voltage surge or voltage transient that could harm the device. So for example, if there's a lightning strike is very, very high voltage. And if that gets onto the line and it's able to pass through your computer, for example, it can destroy your computer or any other type of electrical device that you have on that network. So it's going to be very important that the device could also handle those lightning strikes. And you need to essentially be able to design those parts in or design that AC line filter to be able to handle those very high transients or pulses. Now, what are the primary functions of a safety capacitor? Well, there's quite a few of them, actually. They have to, well, the first is going to be to basically do what we said a little bit earlier, which was to filter out the AC voltages, to basically keep all of the junk from passing from one part to another part, or one device to another device. But they also have to be able to be used in a certain location. So there's going to be certain types of capacitors that are designed for different parts of that AC line filter. And so you have to have a little bit of care in choosing which one to go in each location. Also, you have to know exactly what type of noise, or in this particular case, the differential mode or common mode noise current that you need to be watching out for. And again, to go back to the lightning ordeal, they have to be able to survive very high transients. And you'll see that these particular capacitors later on are actually designed to withstand very, very high voltage transients. And then they also have to be able to essentially not fail. And I'll get to why that's a very important thing. And then the last key component is that they have to meet certain standards. So with safety capacitors, it's not technically a safety capacitor unless it meets an IEC or UL standard. And we get questions from customers quite often about, hey, can I get a UL certification for this particular ceramic or film capacitor? And the problem is it's actually not a safety capacitor. And if it's not designed and qualified or meeting some of those UL or IEC standards, then we cannot provide that. So a lot of care must be chosen or taken by the designer to pick out the right device. And that's a good thing about KEMET. We have a number of field application engineers around the world that are more than happy to help you pick out the right device. So feel free to reach out to me or feel free to reach out to any of them, and we'll make sure that the device that you're designing in is going to meet those standards. So with that said, we're going to lead on to our next poll question. This particular one should be multiple choice.
Yes, so please note that there may be more than one correct answer. So please choose all the answers that you think apply. Which of the following components is used to attenuate common mode noise? And as we wait for the answers to trickle through, Sam, there is one question that came through the chat that was wondering if we're going to address automotive applications in this presentation.
We will. We're actually going to touch on it very briefly. We're going to talk to you about how automotive is very similar to a home in general and all of the appliance and why we kind of need to, consider all of those things as well, because the same types of designs that we would use for a home appliance is kind of the same types of designs that we would hold true for automotive as well, or the considerations at least.
Okay, and I see that the answers still are coming through. We're about close to 70% of our audience having submitted their answers. But more or less, I see that most of our audience today have selected Y safety capacitors, that's option B, and also option D, common mode chokes. Okay, I was just going to ask you what the correct answer is.
Absolutely. So the correct answer is both A and D. So Y capacitors are used for common mode noise, and common mode chokes are also used for common mode noise. X capacitors, on the other hand, are used for differential mode noise, or what is also called normal mode noise, and so is a differential mode choke. And that actually leads on to our next slide, which is how do we reduce EMI on an AC line? And this is a kind of a very important thing to consider. And I guess I should start off by talking about the different types of chokes and capacitors. So as we kind of covered on the last slide, there are differential mode and common mode chokes, and they're used for different types of noise. So there's going to be either the common mode noise or the differential mode noise, which is also called the normal mode noise. So knowing that, there's also two types of capacitors. There's going to be X class and Y class. And they're used for different types of applications. The X class is used typically line to line or line to neutral. The Y class is used on line to ground. The X class is actually used to mitigate or impede the differential mode noise, and the Y class is used to mitigate the common mode noise. So if you look at the example that we're looking at in the middle of the screen, you see that, and this particular example is for an example, a washing machine. And this is a typical AC line filter that's been built for that. And what you see is that the X capacitors are used in conjunction with the differential mode chokes, and the Y capacitors are used in conjunction with the common mode chokes. So a couple of things that I really want to point out here is that for this particular example, the choke is going to have a low impedance at its fundamental frequencies, which are the 50 or 60 hertz that we covered earlier. And that's why it's important to know which countries you're designing these equipments for, because it's going to have a different frequency. So it's going to have a lower impedance at those fundamental frequencies, which is going to allow the useful power that we want to pass through that differential mode choke. But at the higher frequencies, it's going to have a very high impedance, which is going to stop that noise or that EMI from passing through it. On a capacitor, on the other hand, it's going to essentially be the opposite of that. So at the fundamental frequencies of 50 to 60 hertz, the capacitor is going to have a very high impedance, and it's not going to affect that AC voltage. However, but at the high frequencies, on the other hand, it's going to have a very low impedance. And so with the low impedance, it's going to essentially allow that AC voltage to pass through, or it's going to essentially shunt it. So for the X capacitor, which is right here, it's going to shunt it to neutral or to a separate line instead of allowing it instead of stopping it at those higher frequencies. Another thing that I want to mention is that the Y capacitor is connected to ground over here. And so if you think about ground on this particular device, the ground is actually the chassis of the washing machine or the appliance. And that could lead to certain issues. And for example, if that particular capacitor shorts out or if it fails, it's going to essentially fail or short to ground. And so what's going to happen is if someone touches that, it's actually going to lead to them being shocked. And if you get shocked, it can severely hurt you or even cause a death, unfortunately. So it's very important to make sure that these capacitors are selected in order to essentially not fail. And they can fail, but the goal here is to make sure that they don't fail. So it's important to pick out the right safety capacitor. So what is the right safety capacitor? Well, kind of going back through what we've already kind of talked about, the X capacitor is used to protect against the differential mode noise. The Y is to protect against the common mode noise. I kind of already pointed this out, but the X capacitor is designed to be used for line to ground applications. The X capacitor is line to line and line to neutral. And so what we're seeing here is that there are essentially a few, not two subclasses, but subclasses to the X's and to the Y's. And on this slide, we're actually only showing the X1, X2, Y1, and Y2, but there's actually additional subclasses as well, but KEMET doesn't make them. There's the X3, there's the Y3, and the Y4 as well. But I think the more important ones, the ones that a lot of design engineers are going to use, are going to be the Y2s, the Y1s, the X2s, and the X1s. And that's because they're usually used for general purpose appliances such as refrigerators, washing machines, could be microwaves, dishwashers, whatever it may be. And then for, I guess, additional or higher pulse applications, the industrial market, which could be things like industrial lighting ballast or anything that's connected to essentially a three-phase line. So I guess that's the first thing I wanted to point out. And the second thing is starting from the lowest level, the X2, for example, the X2 capacitor is going to have a impulse voltage of up to 2.5 kilovolts. So the part itself is going to be rated anywhere from maybe 250 volts to maybe 310 volts AC, but the part could actually handle up to 2,500 volts of a peak impulse voltage. So again, that's going to be for things like a general purpose application, such as a home appliance. But for the lighting ballast, for example, anything that's connected to the three-phase, they're going to require even higher peak impulse voltages, up to 4 kilovolts, in order to handle the types of voltages that are going to come off of those lines. And then very similarly, we're going to go from a Y2 to a Y1. And so the Y2 is going to be used for peak voltage or peak impulse voltages up to 5 kilovolts. The Y1 is going to be for even higher peak impulse voltages up to 8 kilovolts. One additional thing I want to point out is that sometimes you'll see a capacitor with just an X or X1 or maybe a Y2 subclass. So they're going to have one particular subclass. Every once in a while, you'll come across a capacitor that's going to, for example, on the bottom here, say X1, Y2, and it's going to have X1 for 400 VAC or Y2 for 310 VAC. And that's actually the case for quite a few capacitors, and KEMET actually offers some like this as well, where they actually have ratings for 2 different classes and 2 different subclasses. And that means that the part is actually designed to handle both, in this particular case, the X1 and the Y2. It's actually created to do that. And that's actually going to lead us to our next poll question.
Okay, so our third poll question for today says, can X and Y capacitors be substituted with one another? We'll give it a minute here for the answers to come through. And I see that the answers are fluctuating all over the place, but
all right.
It seems as though that most of our audience is leaning toward answer D, that no, X and Y safety capacitors cannot be substituted with one another. So Sam, what do you think?
Yeah, that's actually very interesting, and I'm actually very happy that we put this poll question in here, because the answer is actually C. Y capacitors can be used in place of X capacitors, but not vice versa, and we'll actually talk about that on the next slide. It does make sense that a majority of you would think that the X and the Y safety capacitors couldn't be substituted with one another. You know, obviously they're going to be different classes, but I guess let's just go ahead and lead into the next slide. You can actually substitute Y's for X's. And the reason being is, if we went back to one of the previous slides where we were talking about the peak impulse voltages, The Y capacitors actually have much higher peak impulse voltages for one, and for two, they're designed for applications that could lead to electrical shock. So if they accidentally failed, or if they were forcefully failed, you wouldn't want to lead to shock. If an X capacitor failed, on the other hand, the only thing that they could lead off to is essentially a fire burning up. So we really need to make sure that the Y2 capacitors are built a bit more robust. And so I guess to kind of go over the substitutions, if you remember correctly, the X1 was the highest rated X capacitor. And so it could only be substituted with an Y1 or a Y2. And as you drop down, the X2 was the next highest. That means that it could be substituted up with an X1, but it could also be substituted with the Y1 or the Y2. The Y2, on the other hand, was a step below the Y1, which means that it can also be substituted for the Y1. But the Y1, since that is the highest rated part on the market, that particular part cannot be substituted with any other device. And so, I guess the answer to that question is yes, safety capacitors can be substituted with one another, but Ys are the only ones that could substitute for X's. X's cannot substitute for Ys, and you actually have to go up in order. So I cannot use a Y2 in place of a Y1. Now, looking at the automotive environments, I mentioned this earlier, but automotive is a very, very big market for KEMET. I think a majority of our sales is toward the automotive market. I know that we have a ton of customers, especially in the Detroit region, and of course, all over the United States and Canada, and even all over Europe as well. And so it's very important to, I guess, kind of talk about the automotive environment. And as you can see here, there's actually an EMI filter that's been built or that are built into automobiles. And you have actually a huge power supply here that includes power factor correction capacitors, DC link capacitors, resonant capacitors, and even output capacitors. But for the purpose of this training, we're particularly looking at the EMI filter, the AC line filter. And so I guess starting with the onboard charger, the onboard charger is essentially like, I guess, connected to the wall. So you could imagine the appliances in your house connected to a wall. And as I mentioned earlier, when it's connected into the wall, we need to make sure that it's not, one, putting the bad stuff back into the wall where it affects other things on that same network, but also it needs to be able to protect from all of that bad EMI from coming into the vehicle. And it also requires, just like the appliances, it also requires the part to be able to, or the EMI filter to be able to withstand lightning strikes or very high transiences or pulses. So the onboard charger has to be designed kind of like that. It has to be able to protect it. For motor inverters, this is also kind of like the lightning as well. Motor inverters could lead to an electrical shock or hazard. And so we have to make sure that they're designed in order to mitigate those effects. And then for fast battery disconnect, that's similar to a lightning strike, or not lightning strike, sorry. That is, well, kind of similar to a lightning strike as well, where we need to make sure that the part is essentially not going to essentially fail whenever the high peak voltages come through. And I'm going to go back to motor inverters for a second because I kind of missaid that. But the motor inverters are kind of like essentially connected to a chassis or ground where essentially if you touch the vehicle, you could get electrically shocked. So the Y capacitor is a very important feature to the motor inverters because they can lead to shock. And sorry about that, I said the two backwards, but the motor inverter leads to shock. The fast battery disconnect, that's essentially like a voltage strike that could damage all of the electronics in the vehicle, and we do not want that to happen. So as you can see here, the AC line filter design is very important for an automobile, just like it is for all the electrical appliances inside of a house. If it fails, it can lead to or if a Y capacitor fails, it could still lead to a shock. If there's a fast battery disconnect, That's essentially like a lightning strike, which will destroy everything inside of that vehicle. And then, of course, since it's designed kind of like or since it's plugged into a wall, kind of like other appliances, that EMI that's coming into the device can, I guess, give it a lot of noise, all of the bad stuff you're wanting to keep out, but also it could also put the bad stuff back onto the network, which we do not want. Now, looking at the types of safety capacitors out there, there's essentially two different types of materials. There's the film materials and the multi-layer ceramic capacitor materials. And then the MLCCs are broken up into the surface mountable devices and then the ceramic discs. So looking at the film capacitors, the first thing you'll notice is that it has a very high operating voltage, up to 760 volts AC, and typically those are going to be the Y capacitors that you'll see that high. MLCCs, for example, the middle section are only rated up to 250 VAC, and then the ceramic disc could actually handle up to 760 as well. So when we're looking at the MLCCs, they're going to be lower voltage type parts. Now, looking at the temperature range, typically they could all handle up to 125. I think most of our film capacitors are limited to maybe 110, but we do have and are working on additional higher temperature parts. The peak impulse voltages of the parts up to 5 kilovolts, so it's 2.5 and 5 kilovolts. But the biggest difference between the technologies here are going to be the next two lines, which are the capacitance and the subclasses. So when you look at the capacitance of a film capacitor in general, whether it's the safety capacitors or whether it's a DC link or whether it's whatever the classes that you're looking for, if it's an AC or DC film capacitor, whatever it may be, whatever you're looking for, the big thing is that a film capacitor is generally going to have a higher capacitance than a ceramic capacitor, and that's actually shown here. So the film safety capacitors are generally going to be metallized paper or film, and their capacitance range from 470 picofarads all the way up to 10 microfarads. An MLCC, on the other hand, whether it's the surface mountable chip or the ceramic disc, it's going to range from 3 picofarads all the way up to 22 nanofarads, with the disc being in between the MLCC's capabilities. And then the final thing is the classes that we're looking for. Again, it's very important to choose the right class because they need to be able to handle the right peak impulse voltages. And they need to not fail, essentially, because if the Y capacitor fails, it's going to lead to a shock. If the X capacitor is going to fail, it's going to lead to a fire, or it could lead to a fire. And so it's important to choose those right classes. So if you need a Y1 capacitor, the Y1 is only available in film. And so the film could actually cover all 4 of the classes that we talked about earlier. The MLCC, on the other hand, the surface mountable device, it's available in X1, Y2 as a combination or X2 by itself. And then the ceramic disc, it's available in X1 or Y2 classes. And there's a few things that gives each of these an advantage over what we just talked about. So the advantage of the film is that we have quite a few automotive grade series, and they also have what we call harsh environment capability. Harsh environment capability is what we call 8585, or the ability to withstand a very high temperature, humidity, and bias. So 8585 is the new standard, and typically it's for 1,000 hours. If your part is 8585 for 1,000 hours, that means it's capable of withstanding 85% relative humidity, 85 degrees C for 1,000 hours, and it's typically a very harsh environment part. And so our film capacitors are designed for both automotive grade as well as the harsh environment capability. And then film capacitors also have the ability to self-heal their dielectric, which coincidentally MLCCs do not. If there's a fault in the dielectric, it's going to stay there. So the advantage of the MLCC surface mountable device is that it's going to be very, very small, and it's going to be high density. If you think about the size of an MLCC, they could get down to, I think, 01005 case size as being the smallest of a typical MLCC. But for a a safety capacitor, I think maybe around a 2220 or 1812 might be the smallest case size. And so the safety capacitor in general is going to be smaller than a film capacitor. And then for the ceramic disc, the biggest benefit here is that it's going to have a slim profile. So if you look at the part from the side, it's actually a very thin part that's able to give you very high operating voltages up to 760. And that's going to be a huge benefit over the 250 you could get out of the surface mountable package. Now, looking at KEMET's film product portfolio, as you can see here, we have quite a few X and Y safety capacitors. Looking at the X's, as you can see here, there's quite a few. I think the more important ones or the newer releases are going to be the R52 and R53 minis. And you can actually see that on the right-hand side of this page. The R52 is a grade 2B, which is essentially an 85/85 for 500-hour part. And it's actually been released. It's on KEMET's website. And the biggest benefit here is that it's a miniaturized device. So when you look at some of our competition, we're going to have some of the same values in a smaller case size. And then additionally, we're going to be releasing the R53 very soon, which is essentially a grade 3B. And again, the grade 3B is the highest temperature humidity bias part that you can that you could essentially offer. And so that's 85/85 for 1,000 hours. And if you look at our Y capacitor portfolio, obviously it's a little bit smaller, but that's because these capacitors are designed to be able to handle higher peak impulses. And so they have to be more conservatively designed. So we're just going to have less of them. But as you can see, we do have X's and Y's. And our focus series or our newest release series is going to be the R41T. That particular part is going to be temperature humidity bias grade 3 as well. So 85/85 for 1,000 hours. But the biggest benefit of this part is that it's 1,000 hours for its AC voltage as well as its DC. And most of our competitions is only going to be for AC. So it's a very cool thing that we went ahead and qualified that part for 85/85 for a DC biased as well. And the other thing is that this particular part is not just a Y or an X capacitor. It is both a Y2 and an X1. And it was made for that purpose. But again, since it is a Y2 rating, it could also potentially be used for an X2. And then additional benefits of that particular part, it is automotive grade qualified, and it is rated up to 125 degrees C. Now looking at our ceramic safety capacitor offerings, as you can see here, we have 3 different series, and KEMET has offered these series for a very, very long time. Again, the big benefit here of using the ceramic disc is that they can handle up to 760 volts AC when compared to the surface mountable chip, which is only up to 250 VAC. But as you can see here, the part is, the offerings that we have is very, very diverse. So depending on what your application is, of course, we're going to have something rated for you. And of course, we don't have an X2, but you can use the X1 or the Y1 or the Y2 in that case. So we do have a very large offerings. One of the questions that we receive very often from our customers is, will you ever design, manufacture any surface mountable chips? And so after quite a number of years of our ceramic team hearing that, we decided to release the CAS, or I call it the CAS series. This particular series is a surface mountable device. It is rated to 250 VAC for X1, Y2 or for X2, and it can handle up to 5 kilovolts of pulse. This particular part does not come automotive grade. And so again, if you need the automotive grade parts, you're going to need to go to a film capacitor, but we do have both the surface mountable and through hole film ceramic capacitors. And again, they do have their own benefits, which are one smaller size or thinner package for the higher voltage, in particular for that leaded disc. So we're going to move on to our last poll question. This particular one is just going to be, I guess, a general question. There's no right or wrong answer here. I guess I'll go ahead and read it for you. David, what type of safety capacitor do you typically use in your designs? Is it going to be film, or is it going to be surface mountable safety? Is it going to be radial ceramic, or is it going to be a combination of the technologies?
Okay, and I see that by far answer A seems to be the popular choice for the audience today, film safety capacitors.
Okay, and I guess how much or what are the percentages on that? I would like to have an idea of
Sure.
who we're talking to.
So about 55 or so percent selected option A. The second most popular choice is option D, a combination of A, B, and or C. About 32% of the audience selected that option. The last one, option D. A smaller percentage selected options B and C.
Okay, awesome. Well, it sounds like a majority of you are using the film safety capacitors, and that's wonderful news. Again, KEMET has a very good portfolio of both the film and the ceramics. Again, our portfolio is very large. Our team is continuously pushing the bounds. So a few of the key takeaways here is that the film capacitors do have the automotive grade qualification for our customers that do require it. And then we're constantly working to improve our devices. And again, the R41T is one of our new focus series, and it's because it's a 125 degrees C part made for those harsh environmental conditions, which is the 8585 for 1,000 hours. And we've released the R52, which is the 8585 for 500 hours. As well as the upcoming release of the R53, which is the grade 3B, which is the 1,000 hour part. And then the other benefits here is that the film capacitors are available in all four of the classes we discussed today, and they are going to have the highest capacity values on the market, or not on the market, but between the three types of safety capacitors we've talked about. And then they have the self-healing dielectrics as well. So if there's a fault, it does have the ability to heal that fault site. Looking at the surface mountable MLCCs, the key takeaways is that they're rated for 250 volts AC, which is going to be a lower voltage, but they do have higher peak impulse voltages up to 5 kilovolts available. They are available up to 125. And if you remember correctly, a number of our films were not rated up to 125, even though we do have some that are. The MLCC isn't available in the Y1 class, and they are going to have lower capacitances. But the benefits here is that they are going to be essentially very small when you compare to a film capacitor. And then the ceramic discs, those have a benefit of having a high voltage as well compared to the film capacitors. They are rated up to 125 degrees C, but they're not available in the Y1 class as well. They do have a low capacitance capacity as well when compared to a film capacity. And then the other thing is that they're going to have a slim form factor. One additional thing, I guess, that I probably should have mentioned earlier, but it kind of dawned on me just now. But if an MLCC is a class 2 or 3 dielectric, such as the X7R, the Y5R, they could have a change in capacitance over their temperature range or a change in capacitance due to a DC bias as well. So it's an additional thing that needs to be considered when you're looking at those types of devices. And there's also a change in temperature as well, the temperature coefficient of capacitance, whereas you go from its low temperature to its high temperature capabilities, there could be a change in capacitance as well. So those are additional things that I think you should take away. And with that, that is the end of my presentation. So I'm more than happy to stick on and answer any questions you may have.
Sure. Thank you very much, Sam, for this very informative presentation. I actually learned a lot from it myself. And yes, we do have a couple of questions that just came in, if you don't mind.
Yep.
The first question says, are ceramic capacitors THB graded? If not, what is the robustness for harsh conditions?
I've never seen at least any of our parts with the THB. Typically, that's a film thing. Um, for harsh environments in general, MLCCs are pretty robust with their design. It's a ceramic material with a electrode material. Usually the electrodes are going to be nickel or silver palladium, silver palladium being the legacy technologies. But the design of an MLCC is generally robust as it is. When we look at a film capacitor, on the other hand, we're looking at a film which is essentially something like polypropylene, which is a plastic with some paper windings inside of a casing. And that casing, if it allows too much humidity or the temperature gets too hot, it could potentially cause the part to fail or to have a shorter lifespan. And so, as the technologies have advanced over the years for the film capacitors, we've been able to essentially mitigate the parts capabilities where they don't have, I guess, much of a humidity problem or a higher temperature problem. And so that's why they typically see the temperature humidity biased effects or the temperature humidity bias grades. And so I guess the answer to that is I've never seen the ceramic capacitors with them. It doesn't mean that they probably don't have them. It's just something that we don't talk about because they're built or the way that they're built is more robust typically than what you would see from a standard film capacitor.
Okay, thank you, Sam. And there are two questions that came while you were answering that question regarding the ceramic capacitors. So I'm going to assume that the two questions are related to the ceramic capacitors here. Yep. The first of these questions asks, can they work at 400 Hertz?
Yeah, so that's an airplane application. And the answer to that is yes, they probably can, or yes, they definitely can. But the key thing here is that, and I guess I should go back kind of and talk about KEMET in general. KEMET, I guess, recommends for airspace or airplane applications a higher reliability grade type component. And when we look at the higher reliability grades that KEMET offers, we go from a commercial grade part up to an automotive grade part, and then a HRA or COTS grade part, military space, and then, customized testing. And so typically, when it comes to an airplane or something that requires 400 Hertz, we typically would want to recommend a higher reliability component. But in a lot of cases, customers want to use the automotive, or in some cases, they don't need those high reliability components. But I think the biggest thing is that a lot of our teams, since a lot of our film capacitors, none of our film capacitors are those higher reliabilities. They stop at the automotive grade, which is in turn its own high reliability. It's a very good capacitor. It's just not military grade, essentially. And so they don't have experience with those types of applications. And so when customers ask data on how the part's going to react at 400 Hertz, we could give them an assumption. It should work pretty well. We just don't have characteristics on what the impedance might be, for example, or what the capacitance might look like, or how different characteristics of those parts are going to change. On the other side of that, our ceramic team has a lot of experience with military grade designs, but the problem is that none of our safety capacitors are even automotive grade. They're all industrial or commercial grade parts. And so again, we don't really have the experience or the data to provide to customers for 400 Hertz. We could definitely provide samples for the customer to test. We do have customers that use the film and the ceramics all the time. It's just something that we don't personally have a lot of experience with. And so I guess the best answer to that question is yes, safety capacitors 100% will work at 400 Hertz. It's just something that we don't have a lot of experience with.
Okay, and with regards to the ceramic capacitors as well, another question asks, what is the failure mode, short or open?
Yeah, that's a very interesting question. So I guess and this is related just to the ceramic capacitor, but the ceramic capacitors in general will inherently fall short. So it's going to be a short circuit in general. There are internal designs that you could do to mitigate that effect, but I believe that the ceramic capacitors that we have don't have that internal design. So there's essentially two internal designs for the parts that you could design in. One is the open mode design, which is where we essentially push in the internal electrodes, where if there is a flex crack or some type of cracking, it shouldn't go across the opposite electrodes. And then of course there's and this is, I guess, related to more in general for flex cracking, but the other design is the serial electrode design, where essentially there's a floating electrode in the middle. So if one side has a flex crack, then it won't go to the other side of that capacitor. Now, if there's I guess a very high voltage and it causes the part to break, in either of those two designs, which is more likely the case to happen in a safety capacitor application, then it's gonna do the exact same thing as a typical design, which is why we probably don't have that internal design on surface mountable safety capacitors, on ceramic safety capacitors. And so I guess the one thing that I should point out here is that a safety capacitor's rating or a safety capacitor isn't built specifically to keep the part from failing, or not from failing. Let me rephrase that. The safety capacitor isn't built to keep it from falling short. The safety capacitor is actually built and rated to keep it from failing. And so it's built to handle those peak voltages, to have those high rated voltages, and to just be able to withstand those very high transients so that they don't fail. It's not so that they fell open or short. A film capacitor, on the other hand, is typically going to fail open, and that's because of its design as well. So an MLCC, if it cracks, the cracks could lead between the different electrodes or through the dielectric to the electrodes, create a conductive path. That will lead to a short circuit. The film, on the other hand, again, it has self-healing capabilities, but they are designed to fail open in general. And that's the case for any MLCC, not just the safety rated parts. And that's the same thing for film, any type of film capacitor, not just the safety rated parts.
Okay, thank you, Sam. And switching gears a little bit from ceramic capacitors to a more general question, are the Y capacitors constructed differently than X capacitors other than having more insulation?
No, I think they're pretty much designed pretty much the same way. It's just if essentially if you look at the design of a capacitor, you have two electrodes on each end and you have a dielectric in the middle. The thicker the dielectric is going to be, the more voltage that it could handle. So it's probably just essentially going to be the insulation that's going to give it essentially a higher voltage rating. And so if I had to guess, that's probably going to be the biggest design differences between the X's and the Y's. There's probably some other subtle differences as well. The types of how we metalize the parts, especially for the films, how the types of metalizations that we use, so single, double, whatever it may be. Also, looking at, I guess, a regular film, and then comparing it to a AC rated film, so a DC to an AC rated film, they use a different type of complete metallization structure. The DC parts use an aluminum metallization. The AC parts use a zinc aluminum metallization. So the metallization materials itself between a regular part, a DC part, and a safety rated part, or just an in general AC rated part, can be different. But when you look at film capacitors as well, the types of metallizations are different because there's some that could have a slope. There's some that could have, different shapes in order to get different current ratings, or different types of, in general, ratings on the part. So there's a lot of different things that we could do for a DC film versus an AC film. And then between DCs and DCs and ACs and ACs, and this is an AC rated part being a safety capacitor. So there's probably quite a few different things that are done to a film capacitor in general. And there's probably very subtle differences between an X and a Y to get you to the higher peak impulse voltages that you see for those Y capacitors over the X's, or to get you from each subclass, the X2 to the X. So I hope that kind of answers the questions. I don't know exactly all of the things that are done. I could almost guarantee you that the dielectric thickness is going to be thicker to be able to handle those higher peak impulse voltages, but If that's something that you would really like to know more about, I could check with our team and get you an answer on that.
All right, thank you, Sam. And I know we're running a little bit over time, but it seems like today we have a very engaged audience, so the questions keep coming in, so we can take a couple of more questions if that's okay with you.
Yeah, just keep them coming. I'm more than happy to stay on as long as I need to for this.
Okay, great. So the next question says, can you comment on capacitance value versus shock hazard currents? And it seems like it's a European IEC standard 60479, also limits in standards.
So I'm not familiar with that standard, and it might be something that I could follow up with our team over in Europe, or even one of our product managers. But I would say in general, the higher the capacitance of the part, the more charge or the more that it could withstand, or the more that it could accept. So with a capacitor, the higher the capacitance, you could think of the capacitance as a water tank. The larger the water tank, the more capacitance it could hold, which is the more charge. So if there's an impulse of current coming through it, it could withstand more of it or absorb more of it, where less is being affected to the dielectric. So I would probably say that most likely the higher the capacitance is going to be better. But you know, when we look at the parts, I think typically when you're selecting the safety capacitor, the most important thing to look at is the voltage rating and the peak impulse voltage of the part. And then from there, the capacitance is really generally chosen to for the impedance over its frequency range. So you would look at the part and determine what its impedance would be over a certain frequency range. And as you go up in capacitance, hopefully I'm saying this right, as you go up in capacitance, the impedance is going to shift essentially to the left or downward toward lower frequencies.
Okay. And the next question asks about really DC applications, and the person that asked the question is wondering, can they use, for example, a 240 VAC safety capacitor for a 300 VDC application? I guess he's just wondering about how he can choose the right capacitor for his DC application based on their AC rated voltage. Is it simply multiplying by the square root of 2?
Yeah, so that's typically something that we say for MLCCs. When you have an AC rated part, there's a specific formula, which is, I think it's the DC voltage divided by the square root of 2. And that should give you your AC voltage capabilities, or your AC voltage capabilities. So when you're going the other way around, you just take the square root of 2 and multiply it by the AC, and you'll find out the DC capabilities of that part. In general, though, there are quite a number. KEMET has a very broad portfolio of DC rated parts. So if it's being used in a DC application, I would probably suggest checking out one of those parts. But typically, yes, the answer is you could take an AC rating and then multiply it by the square root of 2 and come up with the DC rating of that part. And that's essentially what those parts are. I mean, they're higher voltage rated or DC voltage rated MLCCs that were specifically derated to a point where they could handle the voltage capabilities that they needed, as well as there's probably something additional that's done to the design for them to be able to handle those very high peak impulse voltages. But essentially, it's going to be kind of the same thing.
Okay. And the last question that we have time to answer for today is, can you comment on safety considerations of placing 2 capacitors ceramic in series?
If you're placing 2 capacitors in series in general, it's going to increase the voltage capabilities of the part. And so I guess the answer, you know, if you're placing multiple parts in series, you're going to continuously be adding more and more and more capabilities to handle higher voltages. And so I guess in theory, you could probably handle even higher peak impulse voltages. But I guess the other consideration is what's going to be happening to the capacitance, which should be decreasing as you continuously add on more capacitors into that series connection.
Okay, well, thank you, Sam. This is all we have time for today. To our audience, ladies and gentlemen, thank you once again for joining us today. We hope to see you next time. Until then, we wish you the best. Thank you and goodbye. Thank you, Sam. Have a good day.
Thank you, everyone. Thank you, David.
Thanks. Thank you. Bye-bye.